Hey guys, hi, welcome to the session. And first of all, good morning. This is Tejaswi. I have done my master's in chemical engineering from NIT Rourkela, and I have been teaching for GATE chemical engineering students from past 1 year. So now I'm here to discuss a few previous year questions and few topics like few practice questions also. So yeah, so let's continue to the session. And this session is useful for both chemical engineering and mechanical engineering students also, right? So please stay tuned to the session. Yeah. So this question is about a solid sphere with initial temperature Ti is immersed in a large thermal reservoir of temperature Tb. Okay, and the sphere reaches a steady state after a time T1. If the radius of the sphere is doubled, the time required to reach steady state is. Okay, so first of all, from the question, what we are getting the given data? Initial temperature is Ti and it is immersed in a large thermal reservoir Tv. So here we have to determine the time. Okay, and they have given about the time at particular time the temperature of the sphere is. Okay, so T is T1 at particular time T1, right? So by reading the question, what you will get to know? Like these conditions are most these conditions are like suits to lumped heat capacity problem, right? Because we are having a very large ambient air and ambient temperature condition in which we are immersing a solid sphere, right? And it is an unsteady state process, right? So these are the assumptions of lumped heat capacity problem. So according to the lumped heat capacity problem, what is the final equation that we will be getting? Ln of T minus T infinity by T naught minus T infinity, which is equal to minus HAT by MCP, right? So let us derive this, let us define these terms according to the question, right? So T is the temperature at particular time T and T infinity is ambient air temperature. So according to the question, ambient air temperature is Tv, right? So T infinity is equal to Tv and according to the question, the temperature at particular time is T1. So which means T is equal to T1 and initial temperature we have given as T0. In the question it is Ti, right? So Ti is equal to T0. So these are the terms and H is convective heat transfer coefficient and A is the area. So T is the time at what time we are getting this temperature, right? And M is mass of the sphere or mass of the material that we are taking and Cp is the specific heat capacity, right? So these are the particular terms from the equation and from here according to the question what they are asking, they are increasing the radius of the sphere, which means they are doubling the radius of the sphere is doubled. So the time required to reach the steady state is, they are asking about to reach the same steady state, that means to reach the same temperature T1, what is the time required, right? So here this temperature T1 will be the same, ambient air temperature is the same and initial temperature is also the same. And as the materials are not changing, H will be same and specific heat capacity is also same because materials we are not changing any materials. It's just that we are changing the dimensions, right? So LHS of both case 1, if you consider initial case 1 as case 1, so both the cases are LHS of both the cases are the same, right? So we have to equate RHS of both the cases, which means H1A1 T1 by M1 CP1 is equal to H2A2 T2 by M2 CP2, right? So as the materials are not changing, CP1 and CP2 are the same, H1 and H2 is also the same. So now we will be According to the dimensions, A1 and A2 will be different, M1 and M2 will be different, right? So, yeah. So, what is the surface area of a sphere? It is 4 pi r square, right? So, we can write it as 4 pi r1 square T1 by. So, this mass can be given as density is equal to mass by volume, right? So, volume is 4 by 3 pi r cube of a sphere. And will density change? Density of the will be changing if materials are different, right? But here the two materials that we are using are the same, so density will not be different. Okay, so in place of mass you can write density into 4 by 3 pi r1 cube, which is equal to 4 pi r2 square into t2 by density. Densities will be the same, so we can cancel this into 4 by 3 pi r2 cube, right? So 4 pi will be cancelled, or 4 by 3 also will be cancelled, right? So you will be given with r1 square by r3 is r1 cube, right? So you can write it as t1 by r1 is equal to t2 by r2, right? And again his this radius r2 is equal to 2r1, right? So this can be written as t2 by 2r1. So what they are asking, the time required to reach steady state. So if you equate these two equations, you will be getting T2 is equal to T1 by, T1 into 2, right? So as the surface area is increasing, as the surface area is decreasing, the time required to reach steady state will be increasing, right? So this is the answer for the question. So any doubts? I guess you are clear. So let's get into another question. Yeah. So here we are having a walls of cubical oven are of thickness L and they are made of materials of thermal conductivity K. The temperature inside the oven is 100 degrees centigrade and the inside heat transfer coefficient is 3K by L. The wall temperature on the outside is held at 25 degrees centigrade, and what is the inside wall temperature? Which means we are having a oven. Okay, so let us suppose that this is the oven and this is the wall. Okay, so inside the oven, here air will be there, right? So here convective heat transfer will be taking place till the wall, till here, right? So and again inside the wall, conduction. So this is the heat transfer mechanism, right? So, but as it is at steady state, the overall heat transfer that is taking place is equal to the convective heat transfer coefficient or conductive heat transfer coefficient, right? So you can equate it like this, and you will be able to get the answer. So we have cubical oven of thickness L. Okay, so the length of thickness of the oven, walls of the oven is L, and thermal conductivity is K, and the temperature inside the oven is 100 degrees centigrade, which means T infinity. Let us suppose that T infinity is equal to 100 degrees centigrade. Okay, and the inside heat transfer coefficient is 3K by L, which means H is equal to 3K by L. And if the wall temperature on the outside is held at 25 degrees centigrade, means we are having the outside temperature 25 degrees centigrade, right? So we are having enough data for calculating oral heat transfer, right? But we need what is the inside wall temperature, which means we need the interface temperature. It's nothing but interface temperature, right? So here we will be equating Q overall with Q conductive. Okay. As it is a steady state, the amount of heat that is getting transferred is equal. Okay. So what will be the Q overall? The overall resistances will be including convective resistance and conductive resistance, right? So for Q overall, we will be writing delta T by 1 by H L plus It is a rectangular slab, right? So it is x by k. Yeah, it is x by k. Okay. So the heat flux, this is a heat flux. Okay. And this will be 1 by h. Okay. Because Q is equal to HA into delta T for convection. And Q is equal to minus K into dt by dx for conduction. Right. So this is Newton's law of cooling and this is Fourier's law of heat transfer, right? For conduction, we'll be using Fourier's law and for convection, we'll be using Newton's law, okay? So from this, we have enough data. Delta T means the ambient, which is equal to T infinity minus T naught, right? So if you write, you will be getting 100 minus 25 by, what is 1 by h? We have h as 3k by L, right? So we will be writing 1 by 3k by L plus x. What is the thickness? L by k, right? So we have this data which is equal to 75. 100 minus 25 is 75 and we'll be having L by 3k plus L by k, right? So if you bring this L by k value outside, you'll be getting k by L into 75 by 3 plus 1 by 3. So this will be here, right? So you will be getting 3 into 75 by 4 into k by L. Okay, so the heat flux is, for the overall heat flux is this. What will be the conductive heat flux? According to this equation, we will be getting Q is equal to delta T, right? So what is this delta T? It is T minus 25 by x by k, which means L by k, right? So we have to equate these two equations and you will be getting the answer. Okay, so let us equate these two equations. Q conductive is equal to, as Q overall is equal to Q conductive, we have to equate these two equations, right? So T minus 25 by, okay, T minus 25 into K by L is equal to 3 by 4 into 75 into K by L, right? So we can cancel this because K and L are the same, right? Because we have expressed heat transfer coefficient in terms of K and L, right? So then temperature of the inside wall will be given as 25 plus 3 into 75 by 4. So this is the temperature in degree centigrade, okay? Because we have expressed everything in terms of degree centigrade, right? So this will be the answer. Here we haven't converted degree centigrade to Kelvin because we are dealing with temperature difference, right? So temperature difference either in degree centigrade and degrees Kelvin is the same. So that is why we are not converting degree centigrade to Kelvin. Okay. So this will be the answer. I guess you will be able to do the calculations. So please do the calculations and comment your answer. Okay. So this is how we will be solving this problem. And let's proceed to another one. Yeah. So here we are having 150 kgs of water is to be heated in a steam jacketed vessel from 25 to 80 degrees centigrade. Okay, so we are having a steam jacket vessel. Let us suppose that this is a vessel and it is having a jacket in which steam is sent. Okay, so and the temperature of the water. Okay, so we are having the temperature also. So here we are having water and temperature of the cold water, Tc1 at the entrance is 25 and Tc2 at the exit is 80 degrees centigrade. Okay, so we are sending a steam, which means it is, and this temperature is 120 degrees centigrade. So we were sending steam so that it will be condensed, and water will be, the temperature of the water will be increased. Okay, so here there will be the temperature of the steam will be the same for the whole process, which means as it is a high temperature steam, right? So because of this, we will be maintaining we can consider that this is an ambient air temperature. Okay, because we will be observing only phase change but no temperature difference. Only the steam will be condensing from its vaporous state to liquid state. Okay, and the heat transfer area is 0.25 meters square. Okay, so we have heat transfer area which is 0.25 meters square, and the heat transfer coefficients for condensation of steam and heating of water by convection are 1000 and 500 watts per meter square degrees centigrade, right? So we have, which means we can consider that this is the outlet, right, and this is the inlet, right? So H naught for steam is equal to 1000 watts per meter square degree centigrade. Excuse me. And H1 is equal to 500 watts per meter square degree centigrade, right? So we are having different heat transfer coefficients for the same material because the phase is different, right? So water is in liquid state and steam is in gaseous state, right? So as the phase changes, the heat transfer coefficient also changes. So first of all, we have to calculate the overall heat transfer coefficient, which we'll be getting by 1 by U is equal to 1 by H naught plus 1 by H1, right? So from this, you will be getting 1 by 1000 plus 1 by 500. 1 by U is equal to this, right? So U will be equal to 500 into 1000 by 1500, right? So this 103. So which is nothing but 1000 by 3, right? So this can be equal to 333.33 watts per meter square degrees centigrade, because H1 and H2, H0 and H1 has the units in terms of watts per meter square degrees centigrade, right? So here we require find the time required for heating the water, and Cp is also given, right? So I will explain the question and I will explain the conditions of the problem. So after that, you guys just do the calculations and comment the solution. Okay. So when if we see this equation, this is like more equal to lumped heat capacity problem, right? Because we are exposing this water in ambient, a very large thermal reservoir, right? So based upon this, we can consider this as a lumped heat capacity problem, and or you can also equate like Q of convective heat transfer is equal to Q at unsteady state, right? So this can be equal to UA delta T, which is equal to Q at unsteady state is given by MCP dt by dt, right? So we have data required for mass and Cp, and we know what is the overall heat transfer coefficient, and we know what is A, and we know what is delta T, right? So by substituting all these values, you will be able to get the answer. So first of all, let us derive this. Okay. So we have to integrate the equation, which means on integrating, you will be getting UAT by MCP, which is equal to ln of this delta T can be given as T minus T infinity, right? Which means T infinity is temperature of the steam, right? So this T is the temperature at particular time. So ln of T minus T infinity is T1 minus T infinity by T2 minus T infinity, right? So by substituting these values, you will be getting the time required, okay? So after solving, please do comment your solution, okay? So that I will be able to know whether you understood the problem or I should repeat the problem, okay? Yeah, so let's proceed to another problem. Yeah, now we are having a pipe of 25 outer diameter which carries steam. Okay, so we are having a pipe of 25 outer diameter and it carries steam. The heat transfer coefficient between the cylinder and the surroundings is 5 watts per meter square Kelvin. Okay, so it is proposed to reduce the heat loss from pipe by adding insulation having a thermal conductivity of 0.05 watts per meter Kelvin. Which of the following is true? So here, when we are adding an insulation, what we should check first? We should check about critical thickness of insulation, right? So if this is a pipe where steam will be entered in this steam will be going through this pipe, and we are having, so within the cylinder it will be conduction, right? So from the walls to the ambient air it will be through convection. So if we want to reduce the heat losses, then we'll be adding insulation. But to check the point till which we have to insulate the pipe, we will be calculating critical thickness of insulation, right? So what is RC? I will just explain the problem. So you have to comment your answer. Okay, then I will I will also comment back whether it is correct or not, and I will be giving you the explanation also. Okay. So what is the value of what is the formula for critical thickness of insulation? Yeah, it is K by H for a cylinder. If it is for a sphere, it is 2K by H, right? So what is the thermal conductivity? It is 0.05 watts per meter Kelvin, right? 0.05 by 5, which means 0.01 meters, right? Or you can name it as 10 mm because 1 meter is equal to 1000 mm, right? So the critical thickness of insulation is 10 mm, and we are having a outer diameter of 25 mm, right? So the outer radius of the pipe is greater than uh, critical thickness of insulation, right? Which means we are having a double pipe, right? So this is the bare pipe, and here we have insulated with uh, some particular material of heat transfer coefficient, so of these conditions, okay? So we are having the outer diameter of the pipe, which means we are having the data for I mean insulated. After insulation, what is the radius of the pipe? We are having it, right? So and this outer radius is greater than critical thickness of insulation, which means so what do you mean by critical thickness of insulation? So till this radius, the heat losses will be maximum, and after crossing the, if we keep on increasing the radius of the insulated material, then heat losses will reduce, right? So as we achieve this condition, which means the radius of insulated pipe is greater than critical thickness of insulation, automatically the heat losses will be reduced, right? So I have explained the problem. So comment the answer, like whether the outer radius of pipe is equal to critical radius or it is less than critical radius, or adding the insulation will reduce the heat losses, or adding the insulation will increase the heat losses. Okay, so this is about the problem. I guess you have no doubts. So if you are having any doubts, please comment here. Yeah. So these are another theoretical questions. Okay. Yeah. So a hot fluid is stored in a spherical container. So we are having a spherical container and a hot fluid is stored. Okay. In this container, we are storing a hot fluid which has an outside diameter of d naught and inside diameter of di. Okay. So yeah. So this is diameter till here is d naught and inside diameter is di, right? So heat flows through the wall of the container radially outwards. So the radial the heat transfers heat flows through the wall of the container in radial direction, right? So what is the area of the heat transfer? This is a very simple problem. I guess by this time you will be able to comment the answer. So let's just check the comments. So 4 pi root of d1 and d naught, and option B is 4 pi d1 d naught. Option C is pi d1 d naught, and option D is pi into d1 d naught whole square. So if you have attended my course which I am taking in an Unacademy app, so I have started a session for complete course on heat transfer part 1. So if you have attended the session, you will be able to know the answer. Or so if you are not clear about this question, so please do attend. So please do attend the session so that you will be able to answer. Okay. So I'm not saying that this is the correct answer. Okay. I just ticked it. Okay. So comment your answer in the comments. Yeah. So this is like from, in this he is asking about this area. Okay. So what is the heat transfer area in which the heat is flowing? Okay. So yeah, this problem is done, and this problem. Okay. So the wall of an oven consists of 2 layers of insulating bricks. Okay. So these are 2 layers. In between the layers, there is an air gap. So in between this, we are having an air gap. So this is solid S1 and this is solid 2. And in this, we are having air gap, right? So the presence of an air gap will, okay. So by before case was only solids, two solids which are like in series. There was no gap between them. Okay. So second, what happened? So now what they did is they have included an air gap. Means the walls are separated, right? So as the walls are separated, the air gap will be there. Because of which, so what will be the heat transfer mechanism? So this will be like in the first slab, it will be conduction plus in the air gap, it will be convection plus again conduction, right? This is for case 2. In the case 1, it is conduction conduction plus conduction in first case when air gap was not there, right? So if you consider the resistances, here there are only 2 resistances, right? And here there are 3 resistances, means we are adding additional resistance, because of which rate of heat transfer will be decreasing, right? So let us read the options what he was asking. So according to the first option, this because of this air gap, it causes an increase in the heat transfer rate through the composite wall. Okay, and second option is causes a decrease in the heat transfer rate through the composite wall. And third option is have no influence on the rate of uh, heat transfer. Yeah, and fourth option is none of this, right? So yeah, so these are the 4 options. So how you will be deciding whether heat transfer rate increases or decreases? So based on the resistances, you will be able to determine whether the heat transfer rate increases or decreases, because the initial and final temperature conditions in both the cases will be the same, right? But the time required to reach the to reach this steady state or to reach the temperature will be uh, changed, right? So as the resistance increases, the heat transfer rate decreases. So based upon this explanation, do comment your answer. Okay. Yeah, so these are few previous year questions and a few practice questions from heat transfer. So if you haven't taken plus subscription, please do take. And if you want to take the plus subscription, do use my code Padma10 so that you will be getting a 10% discount. Okay. So if you take a plus subscription, you will be able to attend all the weekly quiz, and you will be able to clear your doubts in the doubt clearing sessions, and like you will be having a direct interaction with the educators, which will help you in clearing your doubts. And you can also attend like not only my class, and you will be able to attend other classes also. Okay. So please do take the plus subscription and avail the offer. Okay. So thank you and have a nice day.